All right, so let's talk about circulation. We've already talked about circulation, which is the line integral of a vector field around a closed path. And we've spoken about it so far as something that we have to use an integral to measure, right? Because we have to go all the way around some big closed path in order to measure the circulation. What we're really measuring is kind of what I would call total circulation of a vector field, right? Because it's seeing the circulation of the vector field at a bunch of different points as we wander along that closed curve from some starting point back to the same starting point. What we want to do next is we want to come up with a differential measurement of that circulation. In other words, a way to speak about how a vector field is circulating not over a big closed path, but sort of at a single point. Right? This is sort of typical of what we do in calculus, is we try to take quantities that should be measured on a global scale and measure them at a very local scale, a very infinitesimal scale, a scale that's really close in the limit to a single point. And so when we do that, we're going to get a function that our authors of our textbook call a circulation density. And what it kind of tells us is it tells us whether the vector field has a tendency at each point to sort of spin. If we put a little toy sailboat in the vector field, is that sailboat going to spin in a clockwise fashion, or is it going to spin in a counterclockwise fashion, or is it going to not spin at all if we place it at that point in the vector field? And since this is kind of a challenging thing to study visually, we have, fortunately, the Vector Field Analyzer 2 to help us out with this business. So, for example, if we have this vector field here, sine x plus cosine y, and then sine x times cosine y, this tool actually lets us study whether or not something spins clockwise or counterclockwise. If in the DE's flows tab here, we'll click on curl, we'll click on circle, and then somewhere inside of this flow here, we'll draw a little circle. And so this is my little toy sailboat that once I start the flow, it's going to show which direction the sailboat is going, but it's also going to show which direction that sailboat is rotating as it moves along. So for example, at this particular point, if I start the flow, it looks like as the sailboat moves along, it's rotating ever so slightly counterclockwise. So we would say that in this general area, it seems like the vector field here has a tendency to circulate in a counterclockwise fashion. But that might vary from one point to another. If I pick a point that's over here and I start the flow. Now, at this point, it looks like the tendency is to rotate clockwise instead of counterclockwise. And so our job in the early part of this section is going to be to do some of that investigating using this Vector Field Analyzer 2 tool on a variety of different vector fields and see if we can come up with a way of making that prediction. So what quantity can we compute using a vector field that can tell me about how it's tending to rotate little toy sailboats, how it's circulating in an infinitesimal basis at each different point throughout the xy plane. So your task is going to be to look at each of these four vector fields and decide, will a small spinner that we place at the origin in this vector field spin clockwise, will it spin counterclockwise, or will it not tend to spin at all? And then what if we place the spinner at a different point, at 1, 1, or at negative 2, 1? And are there any points in the xy plane where your answers might be different than the answers that you got for A through C? And so you'll do that for this vector field, the same thing for this vector field, and the same thing for this vector field. And then this last vector field, the questions are just a little bit different. But what I've given you that the authors of our book don't give you is I've given you formulas for these vector fields that will allow you to use the Vector Field Analyzer as part of this process. So for this one, just please write your answers directly next to the questions rather than placing them sort of further down, just so it's easier to look at these a little bit later on. So this is the preview activity for 12.6, and I'll give you 15 minutes or so to be working on. So you're able to find for these first three vector fields that you looked at, these all had a consistent type of rotationalness, no matter which point that you picked. Right? This first vector field looks like it was spinning counterclockwise no matter where we started in this vector field. If we let that little sailboat go, it ended up spinning in a counterclockwise orientation. Meanwhile, the second of these vector fields was not spinning at all, so it didn't tend to rotate our little sailboat in either the clockwise or counterclockwise direction as it moved along, no matter where we started. And the third one also was what we would call irrotational. Sometimes we say irrotational as a vector field that doesn't tend to have either a counterclockwise or a clockwise circulation at any point. So we would call this vector field and this vector field, we would call them both irrotational. But the most interesting example, I think, was the last one, where we could find examples of places where our sailboat rotated clockwise, as well as places where our sailboat rotated counterclockwise, as well as a place where we predict that the sailboat would not have rotated at all. So what you saw, for example, is that if we picked a place in the second quadrant up here, that those places seem to be places where our sailboat was rotating in a counterclockwise fashion, and that if we picked a point in the third quadrant, down here for example, there it looks like we're rotating our sailboat in a clockwise fashion, and that if we wanted to find a place where maybe we weren't rotating at all, that maybe a place somewhere on the x-axis would be a good place, where it seems like it's neither sort of rotating clockwise nor counterclockwise infinitesimally at that point. And so we can certainly have examples of vector fields that do all three of these different types of rotations at different places in the xy plane. And so that's why the tendency of a vector field to rotate really is a function of x and y, or of x, y, and z, or however many variables that our vector field happens to be predicated upon. And so our next step is going to be to figure out what quantity can we attach to a vector field that tells us about that tendency to rotate or not to rotate, as the case might be.